Okay. Right. Good morning, everyone. Okay, today we're gonna try to, of course, start from where we left last time. Do you have any questions before I start myself? Please get going. Anybody? 3140 Austin, and which I imagine this is section 4.3. All right, we'll look at those two problems, which will be basically a reminder of what we did before we left. So let us recall the main idea last time. I mean, those are becoming one of the most important ideas. The following. Okay. So if you have a function f, and if the derivative is positive on an interval, so you have a point, the derivative is positive, the function is rising. The derivative positive, the function rise. The derivative positive, the function rise on interval, then f is increasing on this interval. I stands for interval. If the derivative is negative on the interval, then f, the original function, decreases on this interval. Okay? And those are tools, very important tools that will help us figuring out, algebraically, when is the function positive, when it is negative. So I'm going to start with number 31. Okay. So we have the function f of x equal minus 2 cosine x minus x, but only on the interval 0 to pi. Okay, and the question is, when is it increasing and when it is decreasing? So first we find the derivative, because the axes that will make the derivative positive or the derivative negative are the axes where the function will start increasing. So here the derivative is minus 2 sine x minus 1. We're only interested in this interval. But this is the question. This function, it's hard for us to figure out all the axes that make this positive and negative. So the way we solve those questions is by the following. So basically, that's what I'm looking after. I'm actually solving that, f prime positive, f prime negative. That's really what I'm looking to do. So the way we do it, that's really the approach. We first find the critical point. And remember, those are the point when the derivative equal to 0. Okay, so we're going to do that. Equal to 0. So it's going to give me minus 2 sine x equal to 1. Sine x equal minus a half. It means x equal. So if the sine equal minus a half, let us remember what's the x. Can anybody remember quickly what's x? So you guys start giving me answers. What is x? Anybody knows? So any answers? Help me out. So that's minus a half here. So a half is, that's a pi over 6. So it means I need this angle and I need, nobody's giving me any answer. And this angle. Oh, thank you. So it's pi over 6 plus pi, because I only want in 0 to pi. And pi over 2 pi minus pi over 6. So it's pi plus pi over 6, which is 7 pi over 6 and 11 pi over 6. Very good. All right, now what's the benefit of finding the critical point? Because actually that's what I want. All right, the idea is to follow. We're going to go to what we called last time a number line. So we draw a line. And here I will write the sign of the derivative. And in this problem, because I'm only interested in 0 and 2 pi, I'm going to restrict myself. So not the whole number line. In this particular problem, that's the only thing I'm interested in. Otherwise, there are a lot of other x's whose sign is -1/2. All right, so now I plug in those values. So I have 7 and in order. So 7 pi over 6 is somewhere in here. And 11 pi over 6. Right here, the derivative is 0. And right here, the derivative is 0. And now, what happened in between? The idea is that, so this is my derivative, f prime. At minus the sign of x -1, okay? And the derivative, the idea is that this derivative cannot take a 0 value between 0 and 7 pi over 6. So it cannot be 0 because it's only 0 here and here. So on the interval from 0 to 7 pi over 6, it could be either positive across or negative across. So we pick any point in the interval, and this will be a deciding point. So we need a point in every interval, one here, one here, one here, and we evaluate the derivative. So here, interval, this is a value of x. So 0 pi over 6, 7 pi over 6, 7 pi over 6, 11 pi over 6, and 11 pi over 6, and 2 pi. That's our only hope to find the sign. Okay, between 0 and 7 pi over 6, of course, the easy value is pi over 2. So at pi over 2, f prime is, I plug in pi over 2 in the expression of the derivative, so it's -2, the sign of pi over 2 -1. Sin pi over 2 is 1, so I will have -2, -1, negative. So this is going to give me negative value. Okay, between 7 pi over 6 and 11 pi over 6, so the easy value here is a pi. I plug in pi into the expression of the derivative. I will have -2 sin pi, which is a 0, right? Am I doing any mistake? Are you checking me out? Anybody checking me out? Yes or no? Put it on the chat. Okay. So should I do all kinds of mistakes? Please put on the chat if I am messing it up. So -2 sin pi, which sin pi it's a 0. I will have -1. Pi is less than 7 pi over 6. Oh boy, you see, I told you, I had a feeling I'm doing something very much wrong. So I'll push it to 3 pi over 2. Okay. So at 3 pi over 2, I will have -2 times sine 3 pi over 2, which is -1, which is going to give me +2 -1, which is plus. And between 11 pi over 6 and this, you pick any value, check it out, you get negative. But you guys check it because it doesn't have to alternate. The sign does not have to alternate. Okay, so now I have it. Function decreasing up to here, increasing, and then decreasing. So f decreasing for on the interval 0, 7 pi over 6. F is increasing on the interval 7 pi over 6, 11 pi over 6. And finally, it is decreasing on 11 pi over 6, 2 pi. Okay, so that's really going to be the scenario, right? What value did you put for the last one? Okay, it's a bit tricky. I didn't put anything. I just waved my hand. That's to be fairly honest. I have to pick something between. So you're gonna, one value you can put is something like 2 pi and minus pi over 15. Okay, because it's pi over 6. You wanna take something less than pi over 6. So you can have like 30 pi 30 minus, like 30 by 29 pi over 15. Do you understand what I did? So I waved my hand, to be honest here, because I didn't feel like computing this number. But if you guys have to do it, take away 2 pi minus pi over 15, because here you took away pi over 6. So you need to take away a number which is less than pi over 6. So pi over 15 will do, which is give me 30 pi, 29 pi over 15. And then plug this number into your calculator and you will get a positive number, okay? So you guys don't wave your hand, because what I'm afraid of is that you will be always under the impression that it's positive, negative, which is not right. It doesn't have to be positive, negative, and you're gonna definitely take a problem along those lines, all right? So one more problem along those lines, and I think we will be ready to tackle the other stuff. So let me see, it's number 40. Number 40. So what is it? X squared minus 2 ln of x. So x squared minus 2 ln of x. And this case, okay, there is no restriction on the value of x. All right, so let's do that. Again, I'll start with f prime. For the same reason, I need to solve when f prime is positive. It's 2x minus 2 times derivative of ln of x is 2 over x, okay? And the technique is the same. So I find the critical point. So I'm gonna set f prime of x equal to 0. Now let me note one thing here. Because I'm dealing with ln, it means the domain is positive. It means even if they don't tell me, I should be aware of the fact that x is always positive, because the ln will not take negative value. So we have to be very careful with our x's. Okay, so it means 2x minus 2 over x equal to 0. Okay, so let us solve for x here. I don't know, how would you like to solve for x in here? I usually follow you guys to solve. How would you like to solve? What do you want me to do? Come on, hurry up. Multiply each side by x. Okay, so okay. Or what else? What other approach? You can find a common denominator. So that's another way you can do it. You can find a common denominator. That's one way. So, and then I'll do it the way Elizabeth, I'm not allowed to say your name. Okay, the way your classmate said. So common denominator, it means 2x times x squared minus 2. So the common denominator is x, multiplied by x, divide by x, give me x squared, minus 2, and this is over x equal to 0. Very good. So so this is gonna give me, if this is 0, it means the numerator is 0. It means 2x squared equal to 2. X squared is 1. X is plus or minus 1. Okay? Now, so we have 2 critical points plus or minus 1. So it's gonna give me x is 1 and x is minus 1. But as I said a minute ago, how did you get that? All right, good. I found a common denominator, okay? So let me explain. What does it mean? What's the common denominator? It's x. It means 2x squared over x minus 2 over x equal to 0. Make sense? Okay, now I combine numerator. And then this will give me that. Okay? So that's how I get the x squared. right? And then or, so before I start, or you can go like this, because or to solve it, or you can do that. You can say 2x equal 2 over x multiplied by x. So that's another way you can do it. If you multiply by x, you get 2x squared equal 2, x squared equal 1, x is plus or minus 1. All right, so you can either find a common denominator, or you multiply by x both sides, and then you get x equal plus or minus 1. So you can go either way, because those problems will come up a lot with us. Okay, so now x equal 1, these are the critical point. But this one has to go, because my domain is x positive, because we're talking about the ln. So I have to throw away the negative value. So x equal to 1. Now, and here on my number line, I have to be careful. I put 0 because that's my domain, and this is 1. Now the test point. So x, the derivative, which is 2x minus 2 over x. Be careful, you put the correct value of the derivative, and that's the interval here. So I have 0, 1, and 1 plus infinity. Okay, between 0, 1, a half would make sense. Between 1 and infinity, of course, 2. So here I will get f prime equal 2 times a half minus 2 over a half. So it's going to give me a 1 minus 2 over a half, which is going to give me a 4. So 1 minus a 4, which is minus 3. And it means up to here, my derivative is 0. Now right here, that f prime is 2 times 2 minus 2 over 2, which is 4 minus 1, which is equal to 2. Okay, so my f prime, my function f, so that's the sign of the derivative. It means my f decreases, my f increases. Okay, so we write this down, and then we sketch a small graph. So f decreasing on the interval 0, 1, f increasing on the interval 1 plus infinity. And graphically, let's see how the function would look like. So right here, now I am back to the original function. So now the derivative gave me what I want. I don't need it anymore. Now let me go back to the original function. All right, that's 1 right here. And if x is 1, my original function takes the value 1 minus, that's 0, so it takes a value 1. So it's right there. So that's where I have my horizontal tangent. The derivative is 0 right there. And then it is decreasing up to here. So the function seems to be decreasing up to here. And that is taking off after that. And remember, it never touches the x-axis, the y-axis, sorry, because this you're dealing with a function which is the domain is all the positive numbers. Okay. All right, does this make sense? And the technique, I'm going to use it again also. So it's very important we know this technique. This technique is basic. What we're doing is we're learning how to, if you have an algebraic expression, how to find when is it positive and negative. So the technique, I'm using it for the derivative for any expression. So if you have any expression you're working with, what do I mean by expression? Something like that, minus 3x squared plus 4x. And you want to figure out algebraically when this expression is positive. Okay, you find when this expression takes the value 0, you take the number line, then the number, you divide the number line, the zeros will divide the number line, and then you do the test point, and I figure out when this expression is positive and negative. So it's a technique that's applied to study when something is positive or negative. All right. So now I'm going to talk, I think I talked about it last time, but I forgot basically how well I talked about it. Local max and local mean. I should have listened to my own lecture. Local max and local mean. Okay, right. So I will remind you a little bit actually, and you guys, I remember you guys helped me write down this theorem. Suppose you have C, a critical point. So suppose F has a critical point at C. Critical point at C. Or suppose C is a critical point. It means the derivative is 0. Never forget what a critical point is. A point when the derivative is 0 or the derivative does not exist. That's what critical point is. And so it's a critical point. C, this is 0. So if the derivative changes from negative, for example, to positive at 0, from negative to positive, then immediately we say F has a local what? Max or mean?
Mean.
Mean, yep. Decrease, a local minimum. All right, and if F prime change from positive to negative at C, then F has local max. As I said, I usually, that's how I know this stuff. Local max. If F prime does not change sign, so something like that, it remains positive from both sides. F prime doesn't change sign. Because as I told you, sometimes it doesn't have to change sign. Doesn't change sign at C, then something like this. So positive, positive. So in this case, how is the picture? This is my point C. That's my point C. There is a horizontal tangent, but the derivative is positive both ways. Means it's increasing and it flattened at C, and then it keeps increasing and go up like that. That's how it would look like. Okay, now, if it's negative from both ends, F prime doesn't change, C is neither a max nor a mean. And it's like this, and it's very important to know how to sketch that. Again, that's my critical point right there. And this is my function. It's decreasing. It flattened because the derivative is 0. And then it goes like this. Okay. All right. So let us have a problem to kind of put those ideas together. So let's consider the function. X to the 4 minus x to the 3. And the questions are, find the critical point. And for each critical point, and this test, sorry, I forgot to mention that this is called a first derivative test, because we will study something called the second derivative test. This is called the first derivative test for local max and local mean, first derivative test. So the question here, find critical point, and this, for each critical point, use the first derivative test to decide if it's a max, a local mean, or neither. All right, so here we are, critical point. Critical point, it means you set F prime equal to 0, that's what critical point, and solve for x. All right, F prime. Equal to 0, okay? And remember, the only way to solve, and some of you struggle with solving something simple on the exam, is factoring. Most of the time, solving is really factoring. So here, obviously, I can factor x squared, okay? Especially the problem we give you are basically cooked, so you can factor them. x squared, and this will give me 4x minus 3. So this p equal to 0, it means x equal to 0 and x equal 3/4. Okay. Now the question is, for each critical point, use the first derivative test to decide whether the critical point is a local max and a local mean. So I have to take x equal to 0 and decide if it's a local max, a local mean. So the idea here is that I have to decide whether what happened near 0, what happened to the derivative. Is it going from positive negative, from negative to positive? So that's really what the idea is about. All right, so I can either do them one by one, or it's like what I did before. I will study the sign of the derivative. So actually, I'm going to just study the sign of the derivative once and for all. So sign of f prime. Okay, now it is 0 here, and it is 0 here. And let me take, and then I will study it by itself. Test point x and f prime. Now for f prime, I can use either this expression or this expression, whichever you think it's easier, as long as you don't change it. So this one I actually, that's easier. Minus 3. All right, now the interval. From minus infinity to 0, from 0 to 3 to 3/4, and from 3/4 to plus infinity. Okay. From minus infinity to 0, I will work with -1. This is a half will do, and this is 1 will do. All right, at -1, let's evaluate the derivative. So this is going to give me -1 squared, which is positive, times, I put -1 here, I will have -1, -3, sorry, -4, -3, -7, which is negative. So the derivative is negative. Okay, at a half, I'm going to have 1/4 times 4 times a half, it's a 2, -3. So that's -1/4, that's a negative. And at 1, I will have 4 minus 3, which is going to give me 4 minus 3, which is 1. That's positive. Okay, so of course, x equal to 0. There is no change in sign of the derivative, so it's neither a max nor a mean right there. So x equal to 0, neither a max nor a mean. Not a mean. X equal 3/4, the derivative goes from negative, so the function is decreasing to the left, and then the function is increasing to the right. So it means at this point we have a local minimum. So at x equal to 3/4 local minimum, because f prime changes from negative to positive. It means f change from decreasing to increasing. Okay, and graphically, how's the function looks like? It's going to look like that. At 0, so that's the function. Now I'm down with the derivative. The derivative at 0, we have a horizontal tangent, and the function is decreasing. So decreasing, it means it has to come down here. The derivative 0, it means the function flattens a little bit. And then it remains decreasing. It remains decreasing. At 3/4, the function will climb all over again. And that's the graph that we expect from the function. Okay? Any questions? All right. Today we're going to start, now we're going to start talking about the second derivative. And what does the second derivative tell us about the graph of a function? So I will start here. So local max, local mean is really actually not hard. It's like what we've been doing before. It's a different type of question. So now what does the second derivative tell us about the function? That's the second derivative. Now we barely worked with it, but today we have to start. Tell us about the function. Okay, so first let us remember that what's the second derivative? The second derivative of a function is you start with the derivative and it's the derivative of the derivative. So it's the derivative of the derivative itself. So if you have a function, something that's the original function. So the function goes like that, for example. That's f. So the slope of it is changing. That's the slope. So f prime, of course, is going to be like in this one, the f prime is going to be positive up to here. So it's going to be positive and getting less positive. And I don't know how it looks here, so we're just doing it like that. And then it seems to be getting negative, and then it's back hitting 0. That's why it's the 0. And then it's becoming more and more positive. So that's f prime. But this is again a function. So this is again have its own derivative. Right? So now basically I'm thinking of this as a function, not of that. I think of this as a function. And this one, okay, right, will have its own derivative. That's what's the second derivative. And what can we say about this? Like I did before. Right here, according to my picture at least, it seems to be decreasing. It means the second derivative, that's negative, because the first derivative is decreasing. That's my function. It means its own slope is negative, and then the slope is taking off and it's becoming positive. Okay, so it's the same relationship with f prime to f is the relationship f double prime to f. So just really a little bit to remind us. Okay, right. So now before we come back to this idea, the graph of a function. So far, we really emphasized one aspect of the graph, which is increasing or decreasing. So increasing, rises, decreasing, falls. Now, we need the idea of concave up and concave down. Okay, all right, so a function can increase, okay? Concave up, so that's a function. Concave up, it means it's bent upward. That's concave up, so it's bending upward, okay? So that's increasing, bending upward. Concave down, it means it bent downward. So that's the concavity going down, the curvature of it. So that's concave down, and that's concave up and concave down. So these are the two characteristics of a function. Now, when a function is concave up, it can be concave up increasing, but can be also concave up decreasing. Okay, so that's how it could look like. So here it's concave up increasing, and up to here, okay, it's the concavity up, it has nothing to do with increasing, decreasing, so concave up, but it's decreasing. Okay, now when it's concave down, it could be concave down increasing, then it could be concave down decreasing. It's the same picture. So up to here, that's concave up, increasing, sorry, concave down, increasing, and from here to here it is concave down, but definitely decreasing. Okay, so that's how the graph of a function look like. And any graph is just combination of up, down, or a straight line. So either it's a straight line, if any function, either it's a straight line, or it is a combination of those pictures. Any graph is nothing like a combination of those. Right. Now we're going to study those graphs. We're going to study them very carefully, and we're going to say that what can we say about the derivative and the second derivative in each scenario. And so I'm going to sketch concave up, concave down, and we're going to analyze them the best possible way. All right. So this is concave up, increasing, concave up, so concave up, increasing, decreasing, and this is concave down. Okay. All right. Now, f prime is, in this case, up to here, it's negative. The derivative is negative up to here. And it is positive up to here because the function is decreasing. And the derivative is positive up to here. And it's negative up to here. Okay. So it has, I'm going to analyze f prime a little bit more. So I'm going to kind of analyze this very as clear as possible. So here the function is increasing, means my derivative is positive. Now, right here, up to here, my function is increasing. My derivative is positive. And then my f is decreasing. My f prime is negative. Okay? Now, what I'm going to be interested is in the following question. Is the derivative itself increasing or decreasing? So is the derivative, listen to my question carefully, not positive or negative. Is the derivative increasing or decreasing? So I'm going to look at the easiest scenario. From here and so on. My question now is not a question of positive or negative about the derivative. My question is the derivative increasing or decreasing? So here, f prime, increasing or decreasing? Now I want answers. Increasing. So the derivative now is increasing. Okay, so if you sketch the graph of the derivative, we get an increasing graph. So what can we say about the derivative of the derivative? So this is f prime is increasing. I want to think now. So if you take a piece of paper and sketch the graph of the second, what can it say about the second derivative? Let me ask you a question. If a function, forget about f prime, f double prime. If I ask you the question, if f is increasing, a function, I'm not going to call it f, g. Suppose g is increasing. Then what can you say about its derivative? What info you can say about the derivative? Forget about f double prime. I just want this question. If a function increase, So group, I don't know, increase. What's the thing you get? Positive. That's what you can say. All right, the slope is positive. Yeah. Are you with me? Okay, so if g is increasing, then the derivative of it is positive. All right, now I go back to my scenario. In my scenario, f prime is increasing because that's a graph. I'm just following my nose. I'm sketching those tangent line because that's what the derivative is graphically. Okay, I'm getting those tangent lines. They are rising and rising and rising. So if f prime is increasing, so what can we say about its own derivative? It means, what can we say about f double prime? Anybody would like to answer now? Is it increasing? What's for sure you can say about it? It is increasing. Why didn't tell me here, when I put this in front of you, why you didn't tell me that g prime is increasing here? I ask you if g is increasing. Why did you tell me g prime is only positive? Why didn't you tell me g prime is increasing? You only told me g prime positive. Okay, suppose I take the graph of this function, all right? Suppose this is g. All right, is this function positive, increasing or decreasing? So we have to be patient so we understand this idea. Suppose this is g. This is g. I'm not going to call it f. This is my function g. What can you say about g prime? That's increasing. What can you say about this derivative? It's positive, right? Is the derivative increasing here? Yeah, the derivative is it's positive, right? But it's actually decreasing. So if function is increasing, you know, the derivative does not have to be necessarily increasing. Okay, definitely it does. Sometimes it does. It's not like it's not. It's like in this case. So it's like in this case, it seems to be increasing, but it doesn't have to be because the function can actually becomes like that. And then the derivative decrease, it's positive, but it is decreasing. So the function is actually growing at a slower rate. It doesn't grow by the same speed, but it's really growing. All right. So again here, now I know that the picture is misleading you here. That's really what's going on. So if f prime is increasing, the derivative is increasing, then its own derivative and as a whole doesn't have to be necessarily increasing. The only sure thing, except probably in this picture, but we're trying to actually write a more general situation. But in general, what it can tell you that it is absolutely positive. At least we know that. Okay. All right, let me take this piece, and now this will become clear here. Here, f is increasing. So we're going to study this picture clear. F is increasing, it means f prime is positive. Do you agree on this piece? Now, what about f prime? So f prime is positive, the function is increasing. What can we say about f prime here? Is it increasing or decreasing? In this scenario, what can we say about f prime? Increasing or decreasing? Back to you. Think again. Look at the picture again. Yeah, look at the picture again. Yeah, f prime is positive, but it's decreasing. Yeah, because the slope, what's the slope? It's getting less and less and less and less, heading back towards 0. Okay, so if you look at the picture, it's getting less and less and less, and it's heading towards 0. So f is increasing, so f prime is positive, but f prime by itself, it is decreasing. Okay, so having an increasing function doesn't tell me that, you know, f prime is increasing. F prime could be increasing or could be definitely decreasing. Okay, so when a function increases, the derivative can behave both ways. It doesn't have to behave the same way. The crucial ideas. All right, in this scenario, f prime is decreasing. What can we say about the derivative? The second derivative means, what can we say about the derivative of f prime? In this case. So now think of the derivative as a function. And this function is decreasing. So what can you say about its own derivative? Anybody else? Anybody else? Absolutely negative. So the second derivative here will have to be negative, because if I ask you to sketch the second derivative, the derivative of, if I ask you to sketch the derivative, you're gonna sketch something decreasing like that, because the derivative decrease, so the derivative of that is gonna be definitely negative, all right? Okay, we're gonna study I'm gonna keep analyzing, and if we understand this, it's actually great. We're gonna keep analyzing. I'm gonna analyze from here to here, okay? Yeah, those will get a bit harder, but you will do it. From here to here, I wanna analyze it. It means I wanna know what can I say about f prime. Okay, here we are. Here, the original function. So in this section, and you know, next section and the one after, there are three functions we will be talking about: f prime, and f double prime. And you have to be very clear, what are we talking about? Which one we're talking about? So here, this is my function f. F is decreasing. Okay, f is decreasing. It means the derivative, which is the slope of the tangent line, it's negative. So this one, that's the derivative, that's the slope. Okay, now, the derivative itself, it means those slopes. You just follow the slope. Are they increasing or decreasing? Think a little bit. They are negative. Okay, all right, I'm getting one answer. I want others. Okay, and so I'm seeing the word increasing. Now, why are they increasing? Who can explain that? Why are they increasing? They are negative, but what's happening? They are approaching 0. That's the way to think about it. They are negative, but they are getting less and less and less negative, heading towards 0. So they are negative, but they are getting less and less negative, heading towards 0. So f is decreasing, so f primes, the derivatives, is increasing. Okay, the derivative is increasing. So it's negative, fine, the values are negative, but the derivative is increasing. So now I'm dealing with a function. It's a negative function, but it's increasing. So let's see if I have a piece of paper. No, that's an empty piece of paper. So I have a function now, that's my function g. It is negative, but it's decreasing, increasing, so something like that. So I have a function like this, that's my function g. Okay, negative, but it is increasing. So what can we say about its derivative? Positive or negative? That's the only thing I want. What can I say about the derivative of my g? So it is negative, big deal, but it's increasing. So what can I say about g prime? Absolutely positive. So again here, the g I am talking about is my f prime. That's really my g. So this is f prime, which is my g, is increasing. Means its own derivative is the derivative of it. Its own derivative, which is f double prime, is positive. Okay, so in this graph, when the function is concave up, whether it's concave up decreasing or it's concave up increasing, that's the only scenario possible, my second derivative is positive, and that's crucial. Okay, so the second derivative, having a positive second derivative, is really telling us about the concavity of the function, whether it's concave up or whether it's concave down. That's crucial. Now here, and we're almost done, I can analyze the last piece verbatim. Right here, the derivative is negative. So f is decreasing, f prime is negative. But now f prime itself, is it decreasing or increasing? Now here we know it's very easy because it's losing value. Is f prime here increasing or decreasing? What can you say about the derivative here? Negative, more negative, more negative, more negative, more negative. So if it's -1 here, the derivative, it's -2, -3, -4, -5. So f prime is absolutely decreasing. So f double prime is absolutely negative. So when a function is concave down, whether concave down increasing or decreasing, it doesn't really matter. The second derivative is absolutely negative. Okay, and that's really again, that's very important. So the first derivative, positive or negative, is a question of increasing or decreasing, gaining value, losing value. The second derivative is basically checking, okay, I mean, in the derivative itself, is it increasing or decreasing? So the second derivative, check the concavity, sorry. If the concavity is concave up, we have positive second derivative. Concave down, we have negative second derivative. And this is a big theorem here. The second derivative is positive on an interval, then f is concave up. F double prime negative on an interval, f concave down. Okay. All right, so that's it for today. Your homework will be actually kind of simple for tomorrow. Good luck. I'll talk to you tomorrow. Bye-bye, guys.